All right. This new topic about momentum, impulse, and collision. So, for instance, like if two objects collide each other, and for instance, like what is the impact of one object on the other, and such kind of things can only be explained in terms of kinetic energy and momentum. So in today's topic, the first item that we would like to talk about is momentum. So what is momentum? So if you have an object with mass, like an object, let's say with mass m and linear velocity v, v has a quantity known as like momentum. So by definition, momentum represented by capital letter P, which is a vector quantity, then we are representing it like with an overhead arrow, is equivalent to m times v. As we said, momentum is vector. It's a vector quantity. That means direction is important. Then since it's a vector quantity, then probably like for instance it may have an x component. So if you are trying to find px, if it's like a two-dimensional momentum problem, then you can find it by multiplying the x component of the velocity with m. Likewise, like you can find py, which is the y component of the momentum. Then you can find it by multiplying the mass with the velocity in the y direction. Okay, so since momentum is a product of mass and velocity, then probably it may be somehow related to kinetic energy. As we saw like in the previous chapter, kinetic energy of an object is equivalent to half times mass times velocity squared. As a result, then if an object has a speed or a velocity, and if it has like mass, so therefore it has a kinetic energy. So there has to be some kind of relationship between momentum and kinetic energy. So before that, like let's say like what is the SI unit of momentum? The SI unit of momentum is kilogram meter per second. Okay, and this kilogram meter per second, it doesn't have any kind of special name, just like it's just represented as kilogram meter per second square. So if you look at like now let's come back to the relationship between kinetic energy and so kinetic energy is equivalent to half times mass times velocity square. As we know, like kinetic energy is a scalar quantity, so we're just more concerned about like the magnitude. But from this equation, what we know is like the magnitude of momentum is equivalent to mass times the magnitude of the velocity, or in this particular case the speed. So we can represent like part of the mass times v by p. So the result what you will have is ke equals half times if we represent like one of the velocities by momentum, so what we will have is like half times the magnitude of momentum multiplied by v. Okay, but at the same time you can represent like the magnitude of the velocity or the speed in terms of the magnitude of momentum as the magnitude of momentum divided by m. Just this came just directly from here. Okay, it's not something new. So the result, like if I substitute this v over here, what I'm going to get is then I will have ke equals half times magnitude of p multiplied by the magnitude of p again divided by m. So the result, like kinetic energy is equivalent to the magnitude of the momentum of the object squared divided by twice of the mass. Okay, So this is a relationship between, you know, kinetic energy and momentum. Okay, so the next item probably we are interested in talking about is impulse. Okay, so what is impulse? So impulse is just literally it is the change in momentum. Okay, so for instance, like, you know, you have a golf, and then, like, for instance, like, you know, just you have a golf ball, and then when you hit it like with a golf club, then what happens is, like, you know, the momentum of the ball changes. So initially, like, the momentum or the velocity of the ball was 0, then, but when you hit it like with a club, right? So what will happen is, like, this ball will acquire a final velocity. Then as a result, like, there is a change in momentum of the ball. Okay, so in this particular case, the change in momentum of the ball is equal to the impulse delivered by the player or by the club. Okay, so as a result, like, impulse represented by, you know, capital letter I, okay, is equivalent to the change in momentum. That means momentum final minus momentum initial. Okay, so in terms of mass and velocities, probably, you know, you can write impulse. So impulse equals mass times, you know, v final minus v initial. Okay, so that's what impulse means. Like, but impulse sometimes can have a certain kind of relationship with force. Okay, so how, for instance, now we can proceed to this same equation, and then let's go ahead and then, like, you know, let's go ahead and then multiply this equation by time. Why? Because, you know, in mathematics, like, you know, just if something can produce like a new relationship by dividing both sides of the equation by a similar parameter, then you can go ahead and do so. So if we divide this equation, both sides of the equation, by time, okay, so what we are going to have is impulse divided by time will be equal to mass into v final minus v initial divided by time. But from previous chapters, what we know is, like, v final minus v initial divided by time is what? Acceleration, right? So therefore I over t equals mass times acceleration. Okay, but what do we know about mass times acceleration? What is mass times acceleration? Mass times acceleration is just Newton's second law. Try to remember Newton's second law. Then as a result, like, I over t will result in net force. Okay, so the result, like, impulse can also be found as F net multiplied by time. Okay, so the amount of impulse delivered, you know, to an object is equivalent to the net force acting on the object multiplied by the amount of time, or by the contact time. Okay, so as a result, like, you have, like, impulse equals net force multiplied by time. You know, sometimes, like, you may define Newton's second law, right? So this is just literally, you can define, you know, Newton's second law, like, right? Why? Because Newton's second law states that, like, net force is equivalent to mass times acceleration, right? But now we came up with a new definition for Newton's second law. So what would be that new definition for? So new definition for Newton's second law. Then what we have here is like, the rate of change in momentum is net force. Okay, so net force equals the rate of impulse. Okay, but we know that what impulse is like change in momentum. Okay, so the rate of change in momentum is Newton's second law, okay, which is equivalent to the net force. Okay, so this is what we came up with. Like, for instance, like, it's just sometimes I try to ask this question. For instance, like, you have, consider an egg, right? So consider an egg. Like, let's say you drop an egg. So this is egg, and you drop it on a hard surface. So this is hard surface. And then here you have another egg, probably drop it on a soft surface, let's say on a mattress or pillow, or Then now what would happen is, like, here you let it go, and then when it hits the ground, then most likely it will break. Okay. But on the other hand, when you drop it on a pillow, what's going to happen is, like, this thing is going to have a chance to survive. Okay, so the difference between those two is, the egg was dropped at the same height, right? So if this is height h and if this is same height, so how is it possible, like, it's surviving here, but it's not surviving on the other one? So the main reason this one, you can try to explain it in terms of, like, impulse. Okay, why? As we know, like, for instance, like, impulse, probably, impulse, which is the change in momentum, right, divided by time, is equivalent to the amount of net force experienced by the object. Okay, so the impulse of the impulse is change in momentum. That means it depends on the mass and at the same time the velocity of the object. So since the ball or the egg is falling from the same height, it's going to have, like, the same final velocity. As a result, that's going to have the same kind of impulse, or the same kind of momentum. But the reason is, like, for instance, like, in this particular case, right, there is no cushion. Like, as soon as the ball or the egg drops, and then the contact time between the egg and the hard surface is very small. So this time t is small. So here you have I over t, which is equivalent to net force, right? And same thing here, you have I over t, same thing as net force. Okay, so what happens is, like, in this particular case, right, this time is too short, right? Why? As soon as the ball in the egg falls on the surface, it's just like time is very small, very instant of time. Then as a result, like, your force is really high. So the force that experienced by the egg is going to be really, really large. On the other hand, here, since there is a contact time between the pillow and the egg is going to be, because of, this is a deformable object, as the egg falls, right? So it doesn't get, like, the contact time between the pillow and the egg is longer. So that means this is longer. So there is for the same amount of impulse as in the previous case, but here the difference is you have a larger time of contact between the egg and the pillow. So there is if you have a longer time, then that means this net force is going to be relatively less. Okay, so this contact force is going to be less between the pillow and the egg. Then as a result, the egg will have the chance to survive. Okay, it's just like everything that you see in everyday life, it's somehow related to physics. That's why we call physics is the most fundamental science the most fundamental science. Okay, so this is pretty much like what we really need to know about momentum and impulse. Okay, So probably the next thing that we are interested in talking about is conservation of momentum. Okay, so conservation of momentum. Okay, so the conservation of momentum states that, like, if you have an object, and probably, let's say you have an object that comes in contact with another object, you may call it like, one object is colliding with another object or something like that. Let's say you have a billiard ball which has one mass and it has an initial velocity, right? And then you have another ball that is coming maybe in opposite direction, maybe stopped, or doesn't matter. Whereas this one has its own initial velocity, but it has a second mass. Okay, then this is like before they collide. Okay, then after they collide, you don't know in what direction they move, but it doesn't matter. So probably, like, this guy is moving in this direction, and you can call it like V1 final. And the green ball is going to have its own final velocity. You can call this V2 final. Maybe it's moving in that direction. So then according to the definition of conservation of momentum, what it says is like momentum initial, or the total momentum of a system, right, is always conserved. Okay, so the total momentum of a system is always conserved, even before and after collision. So the definition is like the total momentum of a system is conserved. Okay, so for instance, like if you consider in the previous case, let's say you have mass one which has an initial velocity, right? That's before, right? So, and then after they collided, then you have the second ball, which is like mass one V2 initial. Actually, this is mass 2, right? So this is the momentum before. Okay, so it means you have before momentum, right, before collision. And then you have another one like after collision. Then according to the conservation of momentum, momentum before and momentum after are equal. So that means after the collision, then you have mass 1 that acquired like mass velocity 1 final. Okay, those are vector equations, so keep in mind. Okay, so it's equivalent to mass 1 V1 final plus mass 2 V2 final. Okay, so this is what the conservation of momentum is. Okay, so for instance, in a given system, we're going to see examples in a moment. Then in a given system, like, the conservation of momentum states that, like, momentum in a system is conserved. So you have billiards or cars and colliding, and so the collision, before collision and after collision, what you have is like the same amount of momentum. Okay, then once we start talking about, like, about collisions, then probably the next item maybe we are interested in talking about is like, how many types of collisions do we have then? So in terms of physics, how do we categorize them? So next is like collision. Okay, so, or types of collision. So in general, there are two types of collision. The first one is inelastic collision. Okay, first is inelastic. Okay, so in an inelastic collision, what you have is like momentum is conserved. Okay, so in this one, what is momentum is conserved. Whereas kinetic energy is not. Okay, probably that energy is somehow transferred to something else. Let's say heat or sound, something related to that. Okay, so the other type of collision is elastic collision. So if you have an elastic type of collision, when objects collide, then in this type of collision, what you have is momentum is conserved. Okay. But at the same time, kinetic energy is conserved too. Okay, so this is mostly like, you know, just like, for instance, two billiard balls collided and then like transferred their momentum at the same time they transferred their kinetic energy. That means like the kinetic energy before and after the collision are equal, so therefore that kind of collision is known as kinetic, elastic collision. Okay, so sometimes like probably you may have a special kind of collision. So as an example, like for instance, what if you have a collision, we call it like perfectly inelastic. Okay, so if you have a perfectly inelastic collision, so in a perfectly inelastic collision, what you have is like objects after collision, they stick together and then move together with a common velocity. So as an example, like in our previous case, let's say you have object 1 with initial velocity, and then you have object 2, probably, I don't know, maybe sitting or standing, mass 2, which has let's say v2 initial. Okay, then this is before, and then after they collided, what happens is like they stick together and then they're moving together with the same common velocity. Okay, let's say that common velocity is just v final. So if you look at this, like as we said, you know, kinetic energy is not conserved, whereas momentum is conserved. So there is that, like you will have like a special kind of equation. For instance, what you will have is so what we know is P initial is equal to P final, momentum initial equals momentum final. So as a result, you will have mass 1 v1 initial plus mass 2 v2 initial equals, in this particular case, what you have is the common velocity. So therefore, you'll have mass 1 v final plus mass 2 v final. So v final in the right hand side of the equation, it's a common factor. So therefore, you can take it out. Okay. So then as a result, what you will have is mass 1 v1 initial plus mass 2 v2 initial equals, you know, mass 1 plus mass 2 v final. Okay, so if someone asks you like to find v final or something like that, then you know you can easily find v final. So but this is an equation that you may probably use for a perfectly inelastic collision. Okay, so that's pretty much like the theory that you really probably need to know, like, you know, when we talk about momentum and things like that. Okay, so those are the most ideal scenarios that you have, but the rest is like, it's just, you know, if you go ahead and then practice problems and so on and so forth, then probably, you know, you will realize like how much you can do in this. So having said that, like probably it's time like now to see like some common kind of problems, momentum problems for you know, for this topic. So the first problem states like the impulse experienced by a body is equivalent to its change in what? So we already defined that like impulse is equivalent to the change in momentum, Pf minus P initial. Okay, you know, sometimes some textbooks use just simply delta P, where delta represents change. So, and the next question is the unit of impulse. The unit of impulse is the same as the unit of momentum, which is kilogram meter per second. Okay, this is one. Okay, but the other one is like, if you remember, like we came up with an equation, impulse equals net force multiplied by time, right? So if you look at this, what did they say unit of net force, which is Newton? The SI unit of time is seconds, right? So therefore, impulse can also be calculated, its SI unit can also be equivalent to Newton second. Okay. Then next problem Number 3 states that, as usual, I like to put or list my given parameters. If I need to, try to have a sketch for my problem. Okay, 75 kilogram swimmer, so like dives horizontally off a 500 raft. So I'm going to use different colors. Let's assume that like there is a raft like this, and let's call this mass 1 for the raft, which is 500 kilogram, and then the swimmer is you can consider him as mass 2, or vice versa. He is 75 kilogram. Okay, if the diver's speed immediately after leaving the raft, then let's say, so this is the initial scenario. You can consider this as your initial scenario. He's standing there, the raft is standing there. Then what you can see is like V1 initial is 0, V2 initial is also 0, because both are not moving. But it states that like, just literally tells you the diver is jump off the rafter, okay, with a certain, you can call it like V2 final, and then this guy has V1 final. Okay, because the rafter, like as he horizontally launch himself, like with a 4 meters per second, then V1 final, which is unknown, you're asked to find that. So as we said it, like, in any scenario, what we know is momentum is conserved. Momentum is always conserved. Then as a result, like, you will apply the conservation of momentum equation, which is mass 1 V1 initial plus mass 2 V2 initial equals mass 1 V1 final plus mass 2 V2 final. As you can see in the problem, like V1 initial is 0, then this term will go 0. V2 initial is 0, then this term will be 0. So 0 plus 0 equals 0. We know that mass 1 is 500. V1 final is unknown. Mass 2 is 75 kilogram. Everything is in SI unit, then I don't need to, convert or any of the units. Then you have V2 final. V2 final is it's known, so we're going to substitute it by its known value, which is 4. Okay. Then I'm going to take like known values to one side. So 75 times 4 is known, which is 300. But when I take it to the other side of the equation, it becomes minus. So I have 500 V1 final. So to isolate for V final, I divide both sides by 500. Then this disappears. Then as a result, V1 final will be equal to 300 over 500, which is negative also, 0.6 meter per second. Okay. So what does the negative value tell you? It means the rafter moved in the opposite direction. So when the person jumped into the pool or into the swimming pool or into the river, then the rafter moved in the opposite direction. So the negative value just tells you like the rafter moved in opposite to the person. Okay, so try to understand it from that perspective. So was it a multiple choice problem? So therefore you will go ahead and then choose 0.6 meters per second. The problem needs only the magnitude, then that's absolutely fine. Okay. So if you ever reference it like a textbook, let's say I sometimes use this book by Selwyn, and then go ahead and then like at the end of the chapter there are really interesting problems, and then go ahead and then try to solve. I would go with number 12. No, this one says number 14, but Number 12. On the 10th edition of the textbook. So now the problem, I will try to read it. It says a tennis player receives a shot with a ball. So the mass of the ball is given. Okay, mass of the ball is given as 0.6 kilogram. Travel horizontally, then the ball has an initial velocity of, let's say, 50 meters per second. Okay. And returns the shot with the ball traveling horizontally at, so it has a final velocity, but the velocity is horizontally in the opposite direction, so it is 40 meters per second. Okay. Then now the question is, what is the impulse delivered and by the racket? So question A is asking you, what is the impulse? So it's a very interesting problem. So the problem states, like, you have a tennis player, let's say this is the racket or something like that, and then now originally, like, the ball was traveling like this with 50 meters per second, and then the player kicked the ball back, and then now the ball has 40 meters per second, but in the opposite direction. Keep in mind, momentum is a vector quantity. Then as a result, like, we have to treat it accordingly. So in this case, like, the velocity to the right is 50 meters per second, so therefore I need to represent the 40 meters per second final velocity as negative, because it's because it is moving in the opposite direction. The problem literally states, like, the ball traveled in the opposite direction. So what we know is, like, impulse equals change in momentum. Okay, the change in momentum, that means P final minus P initial. Okay, so P final impulse equals P final means mass times V final. Okay, minus mass times V initial. Okay, then impulse equals M, which is 0.6, multiplied by V final, which is minus 40, and then minus M is again 0.6 times V initial, which is positive 50. Then your impulse is going to be 6 times, that will be minus 24, minus 30. Then the impulse delivered by the player is going to be minus 54 Newton second. Okay, so don't get alarmed. What is that negative impulse? What it tells you is the direction of the impulse delivered to the ball was let me use so the impulse was delivered in this direction, which is in the negative direction. That's it. That's the only reason that, like, you have a negative impulse. Other than that, like, you could assume the other way around. Then in that case, like, the impulse would have been delivered to the right. But in this case, the impulse by the racket was delivered to the left side. That's what it represents. I mean, other than that, like, you don't have to worry much about, like, the why I have this and so on and so forth. Okay. All right, so another problem. Oh, this one has part B. Okay, so probably let's try to do part B as well. Part B it says, like, what work was done. This is a very nice kind of question. So how much work was done on the ball? So always work is defined as, like, you do some work on an object. Work doesn't really happen by itself. Okay, so you have to do it on the object. So therefore, what work does the racket do on the ball? So from a from energy, what we know is work done is equivalent to the changing kinetic energy. Okay. Where did you get this? Probably you may ask that, but the question is like, work done just is defined as sometimes like the changing kinetic energy. This is like, you can prove it. You can prove it like from work, kinetic energy theorem. Okay, there is a theorem that says work kinetic energy. Then as a result, like your work is going to be, half times mass times velocity final square minus half times mass times v initial square. Okay. Then this is the kinetic energy. Actually, it's the negative of the kinetic energy. Then what we know is like what we know is like, for instance, you have the mass, you have the mass of the object. What you have is like the velocity final, you have the velocity initial. So from our kinetic energy theorem, just to make sure that like network is equivalent. No, there is no. It's a positive value actually. So what you have is like half times the mass, which is 0.6 multiplied by final velocity squared minus half times 0.6 multiplied by 50 squared. So you know that like work can be negative even though it's a scalar quantity. Okay, so you can replace those values and then you can get the answer. So there can be 40 squared minus 50 squared. I'm using my calculator. Multiply that. So it's equivalent to negative 270 joule. Okay, so this is the changing kinetic energy of the ball. So how much work is done on the ball? Then you can just claim that like 270 joules of work. Okay, so sometimes like work done by friction can also be a negative value. Sometimes here what we get is a negative work done. So this is the work done by the ball on the racket is this much. But how much work did you do on the ball? Then you can just simply take the positive value of the obtained value. Okay. Then another problem that probably we're interested in solving is problem 22 in your textbook, if you have that text, but it's also interesting. So the problem says you have a rifle with a weight of 30 newtons. So let's consider the rifle is mass 1. So mass 1 is 30 newton. Okay. So, but since it's given in terms of newton, then you need to convert it in terms of kilogram by dividing it 9.8 meters per second square. Okay. Then as a result, like what you will have is 30 divided by 9.8 meters per second square. It's approximately 3 kilograms. Okay. So the rifle is 3 kilograms. Even though it's given in newton, then you need to convert it to mass. And it says like fires a bullet, then you can consider the bullet as mass 2. Okay. Bullet has a mass of 5 gram, which is equivalent to 0.005 kilogram. We need it in SI units to work around. And it says like it has a velocity, mass 2 has a velocity. Then I'll try to explain whether it's initial or final velocity. Is equivalent to 300 meters per second. Okay. Then the question is, part A is what is the recoil velocity? V recoil. So you can imagine it like this. So for instance, before anything happens, you have the rifle, and then you have the bullet inside. Both are at rest. So the result, like what you can say is like V1 initial is 0, and V2 initial is also 0, because it was just at rest. Then now the second step is, now you have the rifle, and then now when the bullet was shot, then it has a final velocity. So V2 final. Okay. Then when the bullet moves to the right, what you are going to get is the rifle moving to the left. So V1 final, which is unknown. So you need to find V1 final. That's what the question is. So this recoil velocity is, in other words, V1 final. So then you go ahead and then apply momentum conservation. So P initial equals P final. So the initial velocity, since the initial velocities were both 0, then you don't have any kind of initial momentum. The initial momentum of the rifle is 0. The initial momentum of the bullet was 0. So there is you have nothing. Okay. Then on the final, what you have is like P M1 V1 final plus M2 V2 final. Mass 1, which is the rifle, which is approximately 3 kilograms, and V1 final, which is unknown, plus mass 2, which is 0.005, multiplied by 300. Okay, everything is in SI unit as we said, equals 0. So you have 0 equals 3 V1 final. Then you multiply 0.005. I think it will be 1.5, right? Okay. Otherwise, you always keep a calculator with you. Just physics is always like as a matter of practicing problems and so on and so forth. Then now take this value to the other side of the equation. As a result, it will be minus 1.5 equals 3 V1 final. Divide both sides by 3 to isolate for V1 final. Then V1 final equals negative 0.5 meters per second. Everything is in SI unit. I'm not worried about like unit conversion or anything. So that negative sign just literally tells you that like when the bullet was moving to the right, then the rifle moved to the left. Okay, that's what it literally is telling you. Just one is moving to the left, the other one is moving to the right. Okay, good. Then the next problem, let's go ahead and then see the next problem. Next problem states a cannon. You can call that cannon probably mass 1, equals 1500 kilogram. Then the shell, which is mass 2, it's 10 kilogram. Okay, cannon of 1500 fires with a velocity, so that means V2 final equals 200 meters per second. Okay, at an angle of 60 degrees above the horizontal direction. Then now the question is find V1 final in the horizontal. Okay, so in this problem, something that you need to pay attention is like it's somehow similar to the previous problem. How? You have the cannon, and you can draw it like this, for instance, and then you have the shell. Then like this is initial condition, okay, which is P initial is 0 because both are arrested, like they're not moving anywhere. But after, what you have is different. What you have is like you have the shell, and now this guy is the shot at an angle of 60 degrees with the horizontal. Now what we are asked to determine is what is this V1 final along the horizontal direction. So what we said is like, it's a vector quantity. This guy is a vector quantity. Momentum is a vector quantity. Then as a result, like what you need is like, you need to have P initial in the X is equivalent to P final in the X. That's how you need to approach the problem. Since both didn't move originally, like before the shot, then as we said it, like momentum initial is 0. Whether it's in the X or in the Y, in any direction, both were sitting at rest, so therefore that is 0. Then let's come to P1 final. I mean P1 final is going to be mass 1 V1 final in the X direction plus mass 2 V2 final in the X direction. Then mass 1, which is 1500, V1 final along the horizontal direction, because you know this is XY, if this is X and this is Y, then the shell is moving along the X direction, along the horizontal, along the ground, across the ground. That's what it literally says. Then you have the shell, which is 10, and then you will have to use V2 final. But keep in mind, V2 final in the X direction has to be equal to V2 final. What was it? You remember the sine or the cosine? Very good. It is the cosine of the angle is what the X component is. So there is a, like V2 fx is going to be 200 cosine of 60 degrees, which is a half, then that's 100 meters per second along the X direction. So 10 multiplied by 100, everything in SI units. Then you move this to the other side of the equation as we did it in the previous problems, then it will be negative. Negative 1000 equals 1500 V1 final along the X direction. To isolate V1 final X, you divide both sides by 1500 by 1500. That erases. Then divide 1000 by 1500. Then what you are going to get is 0.67. So V1 final along the X direction will be equal to 0.67 meter per second. Of course, it's negative, and then keep in mind the negative sign doesn't mean anything else. It just as the shell goes along this direction, along the positive X direction, then the cannon recoiled along the negative X direction. So that's an interesting part of the just the whole momentum thing. Okay. Then let's go ahead and then see another type of questions. So we're trying to see like all varieties of problems, and so that like you will have like an overall understanding of the material. Okay. So now you have a 2500 kilogram truck. We can call that mass 1, which is equivalent to 2500 kilogram, moving at 10 meters per second. So that's its initial. Okay. Strikes a car waiting at a traffic light, then that is like, you can call it M2, which is not known. Its speed is not known, and it's waiting at the traffic. It means its initial velocity was 0. Then after the collision, what happened is both hooked with their bumpers, and they moved together. That means they acquired a common velocity of 7 meters per second. Now what you are asked to determine is what is mass 2. So if you remember, like, just to have you have car 1, or this is mass 2, which was waiting, and mass 1 was coming with a certain initial velocity. And then after they collided, what happened is like they both, their their thing is coupled, and then they're moving together with a common final velocity. So what kind of collision is this? This is a perfectly inelastic collision. So perfectly inelastic. Okay. For a perfectly inelastic collision, if you remember, what we had is mass 1 v1 initial plus mass 2 v2 initial equals the common final velocity into mass 1 plus mass 2, the sum of the two. Mass 1, which was 2500, multiplied by an initial velocity. It had an initial velocity of, what was it, 10 meters per second? Okay. Plus mass 2, unknown. Initially it was at rest, it didn't have any initial velocity. Common velocity 7, then 2500 plus mass 2. Okay. So when you multiply this, what you will have is 25,000 equals, this 7 multiplies everything. Okay, so 7 times 2500 equals 17,500. 17,500 plus 7 mass 2. Okay, then take this to the other side of the equation. Okay, so what you will have is, you will have 25,000 minus 17,500 equals 7 times m2. Then here you'll have 7,500, right? That minus that equals 7 times m2. Divide both sides by 7. Okay, so what you will have is approximately 1071. So it's positive, it's mass, it cannot be negative, so therefore that is what the answer is. Then number 9. So number 9, like we managed to solve like so many questions, which is great. So in the previous problem, like, just if it is a multiple choice, you go ahead and then choose the closest, which is D. Okay. So number 9 states like 2 billiard balls with velocity slowed. So what you have is like, you have those are your given parameters. Let's say v1 initial, we use the blue. Initial is 2 meters per second. That means it's moving in the positive x direction. Then it says like you have another billiard ball which was moving in the opposite direction, which is at 1 meters per second. When they meet in an elastic head-on collision, so elastic head-on collision, so the problem states it's elastic, the collision is elastic. Then what is the final velocity of the first ball? Then v2 final equals actually 1. V1 final equals what? Yeah, when you look at this problem, like at the beginning, probably it's kind of intimidating. I don't know the masses. So first thing that we are going to do is like, we're going to assume both have the same mass. Okay, because there isn't any specific definition. It just simply says 2 billiard balls, and then we're going to use that benefit of the doubt. Like, otherwise we cannot solve it without having a certain idea about the masses. So we're going to assume like, then the thing is, something that you need to keep in mind, there is a magic word in the problem which says, the problem states like elastic. It is an elastic collision. So if it is an elastic collision, then that means both momentum and kinetic energy are conserved. So since this is elastic, then P is conserved and kinetic energy is conserved too. Okay, so let's start with the momentum. So P initial equals P final. Okay, so please pay attention. This is a very interesting kind of problem because it combines both the equations of kinetic energy and momentum. So what you have is m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. So mass is common. We're assuming they are the same, so therefore we're going to eliminate all of them. So what we have is now v1 initial plus v2 initial equals v1 final plus v2 final. The initial velocity of the first ball was given, which was 2. Okay, 2, and then 1. So here the negative sign, don't get confused. The negative sign just means, so the first ball is moving to the right with 2 meters per second, and then the other ball is moving 1 meters per second to the left. So it's just in the opposite direction of the other ball's motion. That's what it means. Then you have v1 final plus v2 final. So 2 minus 1 is 1. Then 1 equals v1 final plus v2 final. What you have here is like just one equation with 2 variables. Mathematically you cannot solve it. So what are you going to do? Well, look for another equation. So where am I going to get the other equation? The other equation has to come from the conservation of kinetic energy. It means kinetic energy initial equals kinetic energy final. So then write the equation. Half times m1 v1 initial squared plus half times m2 v2 initial squared equals half times m1 v1 final squared plus half times m2 v2 final squared. Half is common. You can eliminate the half. Mass is common because they are equal. You can eliminate them as well. Okay. Then the next thing that you will probably need to do is then probably you can substitute all your given values. But instead of doing that, what I'm going to do is the following. So I have v1 initial plus v2 initial squared. So here what I'm left with is v1 initial squared plus v2 initial squared equals v1 final squared plus v2 final squared. Okay. Then what you can do is probably from this equation you can do some kind of rearrangement. So what are you going to rearrange? So probably you can take the ones together. So that means v1 initial squared minus v1 final squared equals v2 final squared minus v2 initial squared. Okay, so by doing that, but what we know is v1 initial squared means v1 initial minus v1 final. Multiply that by v1 initial plus v1 final. Okay, that's what the mathematical equation that you can come up with. Okay, and then on this side, what you will have is V2 final minus V2 initial multiplied by V2 final plus V2 initial. Okay. Then now, you have conservation of momentum. Then you can have conservation of momentum equations. So from the conservation of momentum, like for instance here in this equation, if you remember this equation, from that equation, probably you can have the following: V1 initial, if you take V1 final to the other side, V1 final is equal to V2 initial minus V2 final minus V2 initial. Can you believe that? So from here, what we know is like V1 initial minus V1 final can be substituted as V2 final minus V2 initial. Yeah. So therefore, what you will have is like, you can just bring V1 initial minus V2 final, or the other way around, V2 final minus V2 initial, and then you can substitute that into your equation. So what you will have is like, instead of V1 initial minus V2 final, what I can do is V2 final minus V2 initial. So I substituted this part from whatever I have here into V1 initial plus V1 final equals V2 final minus V2 initial into V2 final plus V2 initial. But you have V2 final here. You can erase this by this. You can divide both sides by the same equation, right? So as a result, what you are going to have is here you'll have V1 initial plus V1 final equals V2 final plus V2 initial. If you collect the initials to one side, so what you will have is V1 initial minus V2 initial. So what I did is I brought this to here and I took this guy to the other side of the equation. What you will have is V2 final minus V1 final. Aha! Now you got two equations. Then now you can solve the problem. Okay. So you can solve it in any way you want. But what we know is like here, if you want, you can also write this as V1 initial minus V2 initial equals. If you take the negative out, what you will have is like V1 final minus V2 final. I want you to have this as an extra equation that you can use for a perfectly elastic kind of problem. Then we are going to use this equation and then we are going to substitute our values. So our values were 2n minus 1. So what you have is here 2 minus of 1 equals minus of V1 final minus V2 final, right? So V2 initial was that. Then you have 2 minus of minus 1 equals 3 equals V2 final minus V1 final minus V2 final. The minus will go and then it's gonna make it. Then this is equation 2. Then combine 1 and 2. Okay, if you combine 1 and 2, what are you going to get? So bring the first equation here, equation 1. 1 equals v1 final plus v2 final. So 1 equals v1 final plus v2 final. Whereas 3 equals minus v1 final plus v2 final. If you add those two simultaneously, what you will have is like this will eliminate. 1 plus 3 will be 4. v2f twice of v2f. Okay. Then divide both sides by 2. Okay. Then as a result, what you have is v2 final equals 2 meters per second. All that. But what you're asked to find is not v2 final. You're asked to find is v1 final. So what is v1 final? You can use just one of the equations, or from equation 1, right? What we know is like 1 equals v1 final plus v2 final, right? So then now back substitute for v2 final, which is just we found 2, and then take 2 to the other side, it's going to be minus. So 1 minus 2 equals v1 final. Then as a result, v1 final equals minus 1 meter per second. Okay. So at the beginning, the problem seems like very intimidating, but don't just be alarmed. Then just solve it. So with this, we are concluding the chapter. I'm sure that you gained all the knowledge that you are looking for in terms of covering momentum, collision, and so on and so forth. So this is like for take your time, come back again and look at the videos again and again and again, and then eventually you are going to get the most out of it. Okay, so with this we conclude the chapter.